Everyone, in this video I'm going to talk through question number 1 from the 2016 AP exam. And so what we have here, our setup is that water is being pumped into a tank at a rate given by this function. And then it's being removed from a tank at a rate modeled by R of t, and we have select values of R of t in the table. So we've actually got two rates here, one that's going in and then one that's coming out. We also have an initial value here. At time t equals 0, there's 50,000 liters of water in the tank. So the first one is a question we've seen a lot at this point. It's estimating a derivative, giving a table of values. And just like we have been, we're going to do that using the average rate of change. So r prime of 2 is approximately r of 3 minus r of 1 all over 3 minus 1. You can grab those tables or those values from the table. And let's see, negative 240 over 2, or just negative 120. And then our units there, we've got liters per hour, or liters per hour squared. And so in this particular year, they gave 2 points for that, 1 for the estimate, and then 1 for the units. All right, now part B says to use a left Riemann sum with the 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. All right, so left Riemann sum, we know how to do real well by now. So from 0 to 1, 1 to 3, 3 to 6, and 6 to 8. And then so left here, I'm going to put in all my left endpoints. So to set this up, I've got 1 times 1340 plus 2 times 1190 plus 3 times 950 plus 2 times 740. And I'm going to type that all into my calculator. And I get 8,050. Now here with units, I'm going to take a close look at our units here. Our base was hours. Whoops. And then our height here, our y values were liters per hour. So when we multiply hours times liter per hour, we should get liters here. So there's the first part, that's estimating that amount of water that's removed from the tank. Now, as far as whether it's an overestimate or an underestimate, we have to see what we know about this function W. Let's see. Actually, I'm sorry, this was the function R. That's the one being removed. So it says R is decreasing on this interval. So since it's decreasing, I can make a little sketch here. If I've got an interval here, a subinterval, a left Riemann sum means that left endpoint determines the height of my rectangle, and we can see that's creating an overestimate. So we should say this is an overestimate because our function R is decreasing and a left Riemann sum is used. Okay. For points for this one, they gave 1 point just for setting up the Riemann sum. They gave a point for that value. and then a point for stating it was an overestimate with your reason. All right, now for part C, we're actually going to skip this one. I should have removed this. This has material from Unit 8, which we know is not going to be included on the exam. So we'll skip that one, and we'll take a look at part D. So part D says, for the interval between 0 and 8, is there a time when the rate at which the water pumped into the tank, and I think that was W. Yep, so I just want to make a note of that. So water being pumped into the tank is W of T. So is there a time when that is the same as the rate at which water is removed from the tank? So R of T. So is there a time when W of T is equal to R of T? Is really the question. Now, if I rewrite this, WT equals R of T means the same thing as W of T minus R of T is equal to 0. Now, when I rewrite it that way, hopefully what we notice here is this is actually an IVT problem. They're asking to guarantee whether this function W of t minus R of t equals 0 on a given interval. So that's IVT. So again, for conditions, if I'm going to use IVT, I'd have to show a couple of things. I need to know, is this function W of t minus R of t, is that continuous? That'd be the first thing. And then I need to know, is 0 between the values 0 or W0 minus R of 0 and W of 8 minus R of 8, right? The function values at those endpoints. If that function's continuous and 0 is between the function value at those endpoints, then we're good to go with IVT. So let's go ahead and take a look and see what we know. Let's see. For R of t, they tell us that R is differentiable. So we know then that R is continuous. Looking at W of t, because that's the way this function is set up, 2000e to the negative t squared over 20, that function is going to be continuous. There aren't any values that make that function undefined. So we know W of t is continuous as well. Since what we have here is the difference of two continuous functions, we know that W of t minus R of t is continuous. So the difference of two continuous functions is also going to be continuous. So we've met our first condition here. Now we're going to look at W of 0 minus R of 0. So I'm going to go back up to my function here. If I plug in 0 for t, I'm going to get e to the 0, which is 1. So 2,000 times 1 is 2,000. So W of 0 is 2,000. Minus R of 0 is 1,340. So that tells me W of 0 minus R of 0 is greater than 0. That one was easy to do. Now we have to look at W of 8 minus R of 8. Well, R of 8 we can get from the table, but W of 8 I'm going to plug into my calculator to get an estimate for that value. So 2,000 times e to the, let's see, negative 64 divided by 20. We get a value about 81.524. So W of 0 is about 81 point, or excuse me, W of 8 is about 82. R of 8 is 700. So if I subtract those, it's pretty obvious that that's going to be less than 0. So then what we know is that 0 is in between those. So we have W of 8 minus R of 8 is less than 0, which is in between W of 0 minus R of 0. So we know it's in between. So now we can use IVT. So we can say, therefore, by IVT, there is a time t in this interval such that W of t minus R of t equals 0. Okay, so there is a time when the rate at which water is pumped in is the same as the rate at which water is removed. So that one you had to kind of dig into a little bit to recognize the IVT. So for points for this one, you got a point here for writing this WT minus R of t equals 0, and then a point for your conclusion stating IVT. All right, that's the end of this problem. Thanks.